Hello friends and my dear students, I welcome you all to my channel. I hope you are all well and your studies are also going on well. This video is part of the playlist CBSE Maths for Class 8 following the textbook of author RS Aggarwal. So this is part 1 video on the chapter of squares and square roots, where I will discuss about perfect squares or perfect numbers and the prime factorization method to verify whether a given number is a perfect square or square number or not. If you are new to my channel or if you are not yet subscribed, and if you are watching my videos regularly and my videos are beneficial to you, then I strongly suggest and request that you please support me by subscribing to my channel, and also please do not forget to press the bell icon so that you will be notified by my future videos. So let's get started with this video. Okay, so I have prepared my notes on today's topic. For the topic of this video, let me check if everything is visible or not. Okay, I hope you can see my notes on the left hand side. On the right hand side, I will do any kind of discussion, and I will also solve the exercise problems of exercise 3A from the textbook of author RS Aggarwal, which is the first exercise on the chapter of squares and square roots. Okay, so what are perfect squares or square numbers? So natural number, I am reading from the notes. So if you wish, you can take a screenshot of my notes on the left hand side, or I will attach the PDF version of my notes in the description below. So what are perfect square or square numbers? A natural number A is a perfect square or a square number if there exists another unique natural number B such that B multiplied by B gives A, that is B square equals to A. So given a natural number, so for example 9 is a perfect square or square numbers. So perfect square or square number means the same thing. So we know that 9 is a perfect square or square number because we know that 9 is 3 multiplied by 3, that is it is 3 square. Similarly, we have 16 is also a perfect square because we can write 16 as 4 multiplied by 4, that is 4 square. Similarly, 121 is a perfect square, as we can write 121 as 11 multiplied by 11. Now remember that for a perfect square, for a perfect square number, there is the number as per the notes. So we have if B square, for a natural number B, if B square is equal to A, then we say that A is a perfect square or square number. Now given A, if you are given A, then the B will be unique. It is not the case that for a given number there exist multiple values of B whose square will give A. No, B will be unique. So that is a perfect square or square numbers. Now the next point is, how do we, given a number, how do we know it is a perfect square or it is a square number? So the method we apply or use is prime factorization method. So as the name applies, as the name says that we have to, given the number, we have to do prime factorization of the number. So what are the steps for prime factorization method to verify a perfect square? The steps are, first we find all the prime factors of the given number n. So if n is the given number, we find all the prime factors of n. Then we create pairs. We create pairs of equal factors from the given prime numbers. Equal pair. For example, let's say the prime factorization of a number. I am randomly taking some prime factors. Let's say we have, for our prime factorization, we have 3 multiplied by 5 multiplied by 3 multiplied by 5 multiplied by 11 multiplied by 11. Now so these are the prime factors of a given number. Now what we have to do is, we have to create pairs of equal factors. That is, pairs of equal factors means this is a pair, 3 3, the factors are equal. This is a pair, this is another pair, this is another pair, and finally this is the third pair. So we will, if we group like this. If we group the pairs, we have like this. We just grouped it. Now we can say that this is 3 square multiplied by 5 square multiplied by 11 square. So we can see, or we can say it that this is 3 into 5 into 11 whole square. So whatever this number is, I don't know, whatever the number is, we can represent that number as 3 into 5 into 11 whole square. So if this is the case, then definitely we can say that this number, whatever this number is, I don't know, this will be a perfect square or square number. So given a number, we will first factorize it. We'll find all the prime factors, and we will see, and we will group, or we will create pairs of equal factors. And if we see that no factor is left behind, no factor is left out, that is, we can perfectly create pairs of equal factors, then that number will be a perfect square or square number. In the notes, the second point says, if the prime factors occur as pairs of equal factors, then n is a perfect square, otherwise n is not a perfect square. For example, if the prime factorization of, let's say, of a number, whatever the number is, let's say if it is 11 into 3 into 11 into, let's say, 5 into 5 into 3. Now we can, now whatever this number is, now if we see, if we can create pairs of equal factors, we will create pairs. So this is the first pair, this is the second pair, but we see that 11 is left out, 11 is left out. So this number is not a perfect square or a square number. So if we can, we will first find the prime factors of the number, and we will try to create pairs of equal factors. And if we can perfectly create pairs of equal factors, and no prime factor is left behind alone, then that number is a perfect square or a square number. Otherwise, it is not a perfect square or square number. So in the notes you can see some examples. 4 is a perfect square because we can create the prime factor. Its prime factors are 2 into 2. So we have a single pair of 2 factors, 2 and 2. Similarly, 9 is 3 into 3. 18 is 3 into 3 into 2. It is not a perfect square because we have a single pair, 3 into 3, and the prime factor 2 is left behind. Similarly, 125 is not a perfect square because its prime factors are 5 into 5 into 5, and we have a single pair, 5 into 5, and 5 is left behind. So it is not a perfect square. I hope you got the idea. Now, so this is one way. This is about prime factorization method to verify whether a given number is a perfect square or not. Now, some results, some are a very important property, or you can say result about perfect squares, is that no perfect square number will ever end with the digits 2 or 3 or 7 or 8. Meaning, if you are given a number, and if that number ends with either of these digits, that is the unit digits, the digit at units place in the given number is a 2 or 3 or 7 or 8, then you can immediately say that number is not a perfect square. Now why is it so? You see that any number, let's say whatever, say the number I am taking, considering a number of 4 digits, where ABCD are the digits 0, 1, 0 to 9. So this is the digits at the D is the digit at units place. Now if I take square of this number, whatever this number is, if I take square, then this whatever this number will be, let's say this number is E, F, G, H, I, J, K. Let's say we have 4 digit number, its square, let's say it is 7 digit number. I'm just taking an example. So the units in the square, the number after squaring ABCD is square in that number, which is E, F, G, H, I, J, K. The unit digit, the digit at the units place is K. Now what are the possibilities of the digit K, given that we are given ABCD? Now K will obviously depend on the digit D, which is the digit at units place of the given number, whose square is E, F, G, H, I, J, K. So if you are given this number, if you are given this number, just by saying k, you can just by saying k, you can tell whether it's a square of any number or not. And just as I say right now, this k can never be the digits 2, 3, 7 or 8. Now why? Now in any number ABCD, the digit at the unit place, in this case D, can only be, the possibilities are 0, 1, 2, 3, like this up to 9. So we know there are 10 digits, so it can only be 0, 1, 2, 3, 4, 9. Now see what is 0 square. Now if I take ABCD whole square, we have the digit k in the square number, squared number, will obviously depend on the digit d. Now, and this k will actually depend on d square. K will depend on d square. Why? Because eventually when we are taking square, we are doing ABCD multiplied by ABCD. We will do this kind of multiplication, and clearly you can see we are multiplying d with d. So whatever d square is, the digit, whatever the d square number is, the digit in the unit place of d square has to be here. Let's say that be x, where x is the digit in the unit place of d square. So definitely, we know that d can only be 0, 1, 2, 3, 4. Now what? Let's see, when we take square of the digits, what are the possibilities? 0 square is giving 0, 1 square is giving 1, 2 square is giving 4, 3 square is giving 9, 4 square is giving 4 square is 16, but we are getting 6. So let me underline the digits on the unit place we are getting when we are taking square of the individual digits. So 5 square, when we do 5 square, we get 25. So the digit and the unit at the units place is 5. 6 square is 36. So the digits at the units place is 6. Similarly, 7 square, we have 49, and the digits at the units place is 9. 8 square is 64. The digits at the units place is 4, and 9 square is 81. The digits at units place is 1. So so you can see, whatever the digit be, that is d, in any given number ABCD, if I take square, then k. So if I take square of ABCD whole square, then if that number is E, F, G, H, I, J, K, the k has to be one of the digits of 0, 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. So these are all the possibilities. From this you can see that the digits of the squares, in the square of the numbers digits, the digits of the unit place is either 0, or it's 1, or it's 4, or it's 5, or it's 6, or it's 7 is not there, 8 is not there, 9. So these are only the possible digits. So what is left behind? What are the digits? What are the digits remaining? That is 2, 3, 7, 8. Hence these digits you will never find at the units place of a perfect square. So if you are given a number, and if you are asked whether it's a perfect square or square number or not, just by seeing the digits of the units place, you can say if it is a perfect square or not. If that digit in the unit place is either 2, 3 or 7 or 8, you will immediately say that it is not a perfect square. Okay, so these are the two small topics that I wanted to discuss in this video regarding a perfect square or a square number. Okay, now let's solve the problems of exercise 3A. Let me quickly check if you can see the problems. Okay, so let's solve now. Some problems will be repeating. Exercise 3A. So the problem number 1 is about Using the prime factorization method, find which of the following numbers are perfect square. For squares, there are 8 numbers. I mean, I don't think I should do 8 numbers, but let's do few of them just to give you an idea how we do it. So the number is 441. So clearly we have to, I'm not arrow, I will do the, let's do the prime factorization first on the rough side, right hand side. If you can do it orally, that is great, but I am not great at doing this kind of prime factorization orally. Now I hope this will divide by 3. So 1 4 47. Okay, now I think it will again divide by 3 4 9. Okay, now I got it, 7 7. Okay, so definitely the prime factorization of 441 is 3 multiplied by 3 multiplied by 7 multiplied by 7, and clearly we can see that we get a pair of 2 pairs of equal factors. So this is a perfect square. So this is a now in short, for perfect square or square number, I am short in writing, this is a PS. Let me first write it so that you can refer it. Perfect square or square number, SN. I am writing SN, which means square number. Perfect square and square number means the same thing. Okay, let's do part 2, 576. Now let me see if I can do it orally. It will divide with, I guess, 4. Yes, it will. If I divide with 4, I have 4 multiplied by 1, 4 and 4. Okay, so 144. Now 144, I know that it is definitely 144 is multiplication of 12 and 12, I guess. I think it's 12 and 12. 24 and 12. Yes, this is 144. My machine is running very slow. This writing is very slow. Okay, so this, now clearly we can see. Now can we are we getting no, because now 4, now it is the prime factorization says that you need to find the prime factors. Now 4 is not a prime number. We can write it as 2 into 2 multiplied by 3 into 4 multiplied by 3 into 4. Now clearly this will not be a, definitely it will not be a perfect square, because we see 12 multiplied by 4 is left behind. Now anyway, if we factorize it further to have prime factors, let's see what happens. 2 into 2, 3 into 3 we can group together. Let's say we are grouping together, 2 into 2 we are grouping together, and what is left behind is okay, so 4 3 3 4 4. How come? Okay, so this is 4 into 4. So we are indeed getting a pair of pairs of equal factors. So this is so 2. So basically this is 2 multiplied by 3 multiplied by 4 whole square. 6 and 24. So let me check. Is 24 square equal to 576. This is 24 into 4 is 96, and this is 48. Okay, yes, so 24 square is 576. So 576 is a perfect square. So this is a perfect square or square number. So okay, because we can clearly see the prime factors, not prime, the factors, the prime factors are 2 into 2 into 3 into 3 into 4 into 4. Now 4 into 4 we can easily write it as 4, we can write it as 2 into 2, and another 4 we can write it as 2 into 2. So definitely it will, 4 into 4 will create 2 pairs of equal factors, whether each factor is 2. So anyway, so we can clearly see we are having pairs of equal factors. So 576 is also a perfect square or a square number, that is, it is a square of 24. Whereas in this case, this was 3 into 7 square, that is, this was 21 whole square. 21 squared is 441. Okay, let's try the third one. 11025. 11025 is a big number, I cannot do it orally. So let's do the prime factorization of 11025. I will divide by 5. This is 2, 2, 0 and 5. Okay, then again I will divide by 5. This is 4, 4, 1. Okay, so this is 5 into 5 into, now this is 5 into 5 into 441. Now this is a pair, and we have already seen 441 is a perfect square. 441 is a perfect square. Now this is 5 square multiplied by 441 was equal to 21 square. So this will be equal to 5 into 21 whole square, or this is equal to 105 whole square. So clearly 11025 is a perfect square. So we have used the result of the fact that 441 is a perfect square, which we have already seen from part 1. So if 441 is a perfect square and 110, and if we multiply 5 into 5, then the whole result will obviously be another perfect square, because we are just multiplying another pair of equal factor. So what I said, okay. So the concept is that if you have, so just a little bit concept which might be very trivial to you, you might have already understood. If n is a perfect square, if you know that a number n is a perfect square, if you multiply with n a number which is a into a, where a is a natural number, so obviously a square n will also be a perfect square. A square n will also be a perfect square. N is a perfect square. You know, n is a natural number. It is a perfect square. And if you multiply a into a, where a is a natural number, then obviously a into n will also be a perfect square, or a square n will also be a perfect square. Okay. So okay, now let's do which one? Let's do 6. Let's do 6. This is 9075. Now let's do the prime factorization of 9075. Let's divide by 5. We have 1, 48, and then 1, then 5. Again divide by 5. This is 3, 15, 31, 6 and 3. Now 363, I think it's I don't know. No, okay. So one thing, okay. So now this is interesting. So we can say that 9075 is 5 multiplied by 5 multiplied by 363. So we have found that 5 into 5 is a pair of equal factors, 5 into 5. But what about 363? 9075 will only be a perfect square if 363 is a perfect square. 90 will be a perfect square if 363 is a perfect square. I hope this is understood, because as I have explained, that if n is a perfect square, then if you multiply a into a, where a is a natural number, then a square n will also be a perfect square. Conversely, if you are given a number a into n, that is a square n, and if you are asked to say whether a square n is a perfect square or not, you can say that this a square n will be a perfect square only if n is a perfect square. So I have 9075 is equal to 5 into 5 into 363. I have already got one single pair of equal factors, 5 into 5. Now this whole thing 9075 will be a perfect square only if 363 has to be a perfect square. Now we know that 363 is not a perfect square as it ends, sorry for my very bad handwriting, ends with the digit. I've already explained that any square number cannot have the digits 2378 ending with the digits 2378. That is, the digits 2378 cannot be at the units place of any number, any square number, as it ends with the digit 3. So 363 is not a perfect square. So if 363 is not a perfect square, so definitely the number 5 into 5 into 363 will also be not a perfect square. So this is not perfect square. What about 1089? Let's see 1089. 1089. I have no idea why my machine is running so slow. Let me give me a minute. Let me stop a few processes. I'm stopping few servers which runs default. Okay, this might help a little bit. Where is my pen? Okay, so 1089. Okay, so let's see what is the prime factorization of 1089. Will it of 1089, will this divide by 9? Will this divide by 3? Now I am not really familiar with the concepts of which numbers are divisible by 3, 5, 6, 7. So there are some concepts from the chapters playing with numbers, where you can say just by saying the last two digits or the last three digits or even the last digits or even the sum of the digits, and you can say whether this whole number is divisible by 3, 4, 5, 6, 7, 8, 9, 10. So 9. Will it divide by 3? Yes, it will divide by 3. So 3, 6, 3. Oh, okay. Now here is a tricky problem. Now, so we can see that 1089 is 3 into 363. Now you know that 363 is not a perfect square. We have seen 363 is not a perfect square. Where we have seen, oh sorry, 363 is not a perfect square because it ends with the digits 3. Now if we multiply 3 with it, if we multiply 3 with it, then never say that this whole number is not a perfect square because 363 is not a perfect square. The only reason, the only thing I explained was that if you multiply number a into a with n, that is a square n, then if n is not a perfect square, then a square n will also be a not perfect square. And also if a square n will be a perfect square only if n is a perfect square. So now we have to do we have to find actually the prime factorization of 363. So this is 121, and definitely 121 I know it's 11 and 11. So we can clearly see that 363 is nothing but its prime factorization is 3 multiplied by 11 into 11. So we clearly see pair of equal factors. So this is 3 multiplied by 11 whole square, or this is 33 whole square. So this is a perfect square. Okay, I will not do the rest of the parts of problem number 1. I will go to problem number 2. So show that each of the following numbers is a perfect square. In each case, find the number whose square is the given number. So it is asking, so we are given a some numbers. We have to verify whether using prime factorization method we have to verify, or other methods we have to verify whether a is a perfect square or not. if it is a perfect square, then we have to find b. We have to find b such that b into b equals to a, or b square whose square is the number a. That number we have to find. Let's do part 1, that is 1, 2 to 5. So let's do the prime factorization of 1, 2 to 5. Let's divide by 5. So we have 2, 4 and 5. And let's divide again by 5. We have 49. So 49 we know is 7 and 7. So we have, this is 5 into 5 into 7 into 7, that is, this is equal to 5 into 5 into 7 into 7. We can clearly see it can, all the factors, prime factors, can be considered as a product of pairs of equal factors. We have two pairs. The first pair, in the first pair, the equal factors are 5, and in the second pair, the equal factors is 7. So clearly, now we can see that if we rearrange this, the product of these prime factors, we see 5 into 5 is 5 square, and we have 7 square. Now using the laws of exponents, we can say that this is 5 into 7 whole square, or this is 35 square. So clearly b is 5. So first of all, this is a perfect square, this is a perfect square, and we can see, so in each of whose square is the number, so we can clearly say that 35 square is 1, 2 to 5. So 35 is the number whose square is 1, 2 to 5. Okay, let's do part 3. Now I do not think I need to solve the rest of the problems. You got the basic idea. Even though you can do it on your own, I am pretty sure about it, but let's do some more problems. So part 3 is 5, 9, 2, 9. So let's find out the prime factorization of 5, 9, 2, 9. Will it divide by 3? No, I don't think so. 27. No. 9. 9. No. 7. 7, 56, 3, 24, 8. No. Prime factorization 7, 49. 7, 56, 32, 28, 69. No. 3, 27, 22, 1. No. Definite, so that each of the following numbers is a perfect square. Okay, so it is a perfect square. What can it be? 13, 17. Now 17, 3, 54, 5, 54, 52, 17. Now how do we actually find a square root of a number? There is a method. (11), 55, 42, 33. Oh, okay. I think it's dividing by 11. Let's see. 5, 55, 4, 42. So 3, 33, and 42, 9. So 9. Okay, 539. And 539 is it okay? So 539. Now will it divide by 44? Yes, it is again dividing by 11. Now since it is given that show that each of the following numbers is a perfect square, so if 5929 is dividing by 11, there has to be another factor of 11, because definitely 5929 will have a pair where each factor is 11. So we have 44, 44 and 9, 9, and then we have 7, 7. So we have 11 into 11 into 7 into 7. So this is equal to 11 square multiplied by 7 square. This is equal to 11 multiplied by 7 whole square. So this is equal to 77 whole square. So we clearly saw that 5929 is definitely a perfect square, because we can clearly see pairs of equal factors. This is one pair and this is one pair, and 5929 is the whole square of 77. Okay, what else? Let's do 7056. 7056. So prime factorization, let's find the prime factorization. 70, so definitely this is dividing by 7. 10, 0 and 8, I guess. Yes. What about this 1008? Where it divide? So now when it is given that we have to show that 7056 is a perfect square, and whose square is this number 7056. So if we see that 7 is a factor of 7056, definitely 7 will also be a factor of 1008. So we can easily divide by 7. So this is 1, 38, 4 and 4, and clearly we see this is 12 and 12. So we can say that 7056 is, even though we are not actually doing prime factorization, because the prime factors is 12 is not a prime number, it has to be expressed as 4 in 2 into 2 into 2 into 3, but I hope you are getting the idea. So this is, we can clearly see, is 7 into 7 multiplied by 12 into 12. So clearly we see it is a product of pairs of equal factors. One pair is the 7 into 7, another pair is the 12 into 12. So this is nothing but 7 square multiplied by 12 square. This is nothing but 7 into 12 whole square, and 7 into 12 is 84 square. So this is definitely PAS, perfect square, and the number whose square is 7056 is 84. Okay, I will not do the rest parts of the problem 2. I will move to part 3. Sorry, not part 3, problem number 3. Now problem number 3 and 4 are very interesting. These are a very special type of problem. You should be very well aware of solving this kind of problem. So problem number 3 says, by what least number should the given number be multiplied to get a perfect square number? In each case, find the number whose square is the new number. So it is saying that 3675, this is the number. By what least number, this number, that is 3675, has to be multiplied so that the result becomes a perfect square. So definitely it means that 3675 is not a perfect square. Now how do we find the least number that need to be multiplied with this number to give a perfect square? So we have to first find the prime factorization of 3675. So let's divide by 5. This will be 7, 2 and not 2 but 3 and 5. So 7, 5, 7, 35, 15. Okay. So let's divide again this by 5. We get 1, 2, 7. Okay. Not 1, 2, 7, but I'm doing some very silly mistake. This will be, let me check once again. I'm very prone to do make silly mistakes. Okay, so 5, 7, 35, 1, 3, 15, 25. Okay, 23, 4 and 7. Now this will divide by 4, 3, 4, 12, 9. This we know that this is 7 into 7. So we can see that 3675 is 5 into 5 into 3 into 7 into 7. Now let's create the pair of equal factors. This is one pair of equal factor and this is one pair of equal factor. So we can see that 3 is left behind. 3 is the left behind. So this is 3675 is definitely not a perfect square. Now how by what number we can multiply, by what least number we should multiply this whole 3675 to give a perfect square. Now clearly we can see, if we can somehow make the 3 a pair, if we multiply with 3, then we are completing the pair 3 into 3. This will make the number a perfect square. So the idea is that you do the prime factorization, and whatever number is left behind, whatever factors are left behind, all those factors are not actually part of any pairs. You have to multiply those numbers, those factors again with that number to give a perfect square. So what do I mean? So in this case we have to multiply 3, 6, 7, 5 multiplied by 3 will give a perfect square, which is equal to, will be 5 square multiplied by 3 square multiplied by 7 square. This is equal to 5 into 3 into 7 whole square, and this is equal to 15 into 7 whole square, and this is equal to 105 whole square. Now 105 whole square, whatever the number is, that is the new number. What is the new number? The number that we have found by multiplying 3675 with 3. Now why 3? Because we see from the prime factorization of 3675 that in the prime factorization only the digit 3, only the number 3 is left behind, and the other factors are clearly making pairs of equal factors. 5 into 5 and 7 into 7, they are making pairs of equal factors. Only 3 is left behind. So if we can somehow multiply with 3, just by 3, then we will get another pair 3 into 3, which will make this whole number a perfect square. So we have to multiply 3675 with 3 to make it a perfect square, and the new number becomes 3675 multiplied by 3, which is actually 105 whole square. So we were asked to find, so the answer is 3, and find the number whose square is the new number. So that number whose square is the new number is 105. So these are the two answers that are asked. First we have to multiply the given number with 3, that will make a perfect square, and whatever the perfect square is the new number, that is the square of 105. Now what I was saying is that, let's say you have some, you did a prime factorization of some number. Let's say the prime factorization come out to be a multiplied by a, and let's say b multiplied by b, let's say c multiplied by c, but you do not have a pair for d, you do not have a pair for e, and you do not have a pair for f. So you have 3 pairs, and three factors which are left behind. So whatever this number is, this number will be given to you, and from that number you found that the prime factorization is coming out to be a into b into b into c into c into d into e into f. So you can see that there are 3 pairs of equal factors. One pair is a into a, second pair is b into b, third pair is c into c, and you see that 3 numbers are left behind, d into f, d into e into f. So what will be the least number? You should multiply this number, whatever this number is, so that it will become a perfect square. That number will be d into e into f. Only then you will create pairs. Only then you will create another 3 pairs, that is d into d, e into e, and f into f. So that is the idea. Okay. Now let's do another part. Then it will be clear. Let's do 7. Part 8. 2475. Let me see if it's all visible to you or not. Okay, 2475. So first we have to find its prime factorization. Okay, so 2, 4, 7, 5. Let's divide by 5. We have 4 and then 9 and then 5. 4, 47. Okay, then we can again divide by 5. We have 95. No, 9, not 95. What I am doing? This will be 45, 9, and we can clearly see 9, 11. So the prime factors are 5 into 5 into 9 into 11. We can clearly see we have only a single pair of equal factors. These two are left behind. So what is the number? What is the least number that we should multiply 2475, which will make it a perfect square? That number to be, please remember, this is the least number, least number to be multiplied is equal to 9 into 11, that is 99. Now if you multiply, if we multiply 2475 with 99, what are we getting? We getting 5 into 5 into 9 into 11 into 9 into 11. So this is equal to 5 into 5 is the first pair of equal factors. Then we have 9 into 9, the second pair of equal factors, and 11 into 11, the third pair of equal factors. So this is 5 square multiplied by 9 square multiplied by 11 square. This is equal to 5 multiplied by 9 multiplied by 11 whole square. Now what is 5 into 9 into 11? 5 into 9 into 11. So 99 into 5. 99 into 5 is definitely 495. So the new number that we got by multiplying 99 with 2475, whatever the number is, that will be the square of 495. So the answers are 99 is the number that we should multiply 2475 to make it a perfect square, and whatever the new perfect square we are getting, that is a new number, that number is the square of 495. These two are the answers asked. I will not do the rest parts of this problem. I hope you got the basic idea of how to solve this kind of problem. That is, what least number should be multiplied to a given number which is not a perfect square to make it a perfect square. Let's do the the next very typical problem, that is by what least number should the given number be divided. So the previous one we were asked what is the least number we should multiply a given number to make it a perfect square, and in problem number 4 we are asked what is the least number we should divide the given number to make it a perfect square. Let's do part 1, 1, 5, 7, 5. So definitely in both these kind of problems you definitely have to find the prime factors. Okay, can you see the problem number 4? No, you cannot see. Okay, how can I make give me a moment please. Okay, so we have to find the prime factorization of 1, 5, 7, 5. This is the first task. Let's divide by 5. We have 3, 1, 5. Then again I will divide by 5. This is 63, and this we know is 9, 7. So this is equal to 5 into 5 multiplied by 7 into 9 is 3 into 3. So definitely this is not a perfect square because we see that 7 is left behind and we see two pairs of equal factors, that is one pair is 5 into 5 and the second pair is 3 into 3, but the number 7 is left behind. Now this question is saying what is the least number we should divide this whole number so that it becomes a perfect square. Clearly this is the number that we should divide. It is very interesting if you see that in both the problems the answer is coming out to be same. In the previous problem it was asked what is the least number that we should multiply. In this case, if you multiply by 7, 7 is the least number that you should multiply with this number, which will make a perfect square. Also 7 is the least number which you divide. If you divide the number, given number 1575 with 7, then also it will be a perfect square. So definitely 1 5 7 5 divided by 7, it will give 5 multiplied by 5 multiplied by 3 multiplied by 3, this is 5 square multiplied by 3 square, this is equal to 15 square. So the answer for this question asked two things. What is the least number that you should divide the given number 1575 to make it a perfect square, and the second thing it asks is that after dividing whatever the new number is that is a perfect square, you have to find whose square is that perfect square. So the answer for this question is 7 and 15. So these are the two questions. We should multiply the given number by 7, and after dividing the given number by 7, we get a number which is a square of 15. Okay, let's do part 7, which is 8820. Let's find what is the prime factorization of 8820. Let's divide by 2. So 4410. Again let's divide by 2. So 2205. Then let's divide by 5. We have 441. Now 441 we know. Okay, so this is 2 multiplied by 2 multiplied by 5 multiplied by 441. So we are taking actually help from some previous example. The problem number 1, part 1, we saw that 441 is the square of what number? 21 square is 441. 21 square is 441. So this we know is 2 into 2 into 5 into 21 square. Now we can clearly see that what will be the, let's write 21 multiplied by 21. So we have 8820. We can see if you do the factorization, we have one pair is 2 into 2, other pair is 21 into 21. So we can clearly see that the only number which is left behind, which is not creating a pair of equal factors, is the number 5. So we have to divide this whole number 8820 by 5, and then we will get 2 into 2 into 21 into 21, which will be a perfect square. So 8820 divided by 5 is 2 into 2 into 21 into 21. This is equal to 2 square multiplied by 21 square. This is 42 whole square. Okay, so we can say that the answers are 5 and 42 because 5 is the number by which we should divide the given number, that is 8820. If we divide 8820 by 5, we get 2 into 2 into 21 into 21, which will be a perfect square. So the new number after dividing the given number by 5 is 2 into 2 into 21 into 21, which is nothing but 42 whole square. So 5 and 42 is the answers. Okay, I think you can do the rest parts of the problem 4. Now I will do problem number 5. Problem number 5. Can you see problem number? Okay, you can see it. Problem number 5 says, find the largest number of 2 digits which is a perfect square. What is the largest number of 2 digits which is also a perfect square? The largest number of 2 digits is 99. Largest number of 2 digits is 99, which is not a perfect square. Okay, so we have to find the largest number of 2 digits which is a perfect square. Now consider, so we the one way of solving is that you keep on considering those numbers whose square will be less than equal to that is, find a, which is a natural number, of course, natural number such that a square is less than equal to 99. Now if you can find that a whose square is 99, then you can clearly say a 99 is the largest 2-digit number which is a square, but obviously 99 is not a perfect square. So what we can do, what is happening in my machine? Okay, so how we need to find a, we need to find a such that, because we need to find a such that a square will be less than equals to 99. Now what can be a? 2-digit. Now a number whose square, how many digits a can have? If a square is digit, if the number a square, if the number of digits has to be 2, then the number of digits in a cannot be more than 1, because if it's more than 1, 10, we are getting 10 into 10, 100. So it is crossing 2-digit number. So we can see 9. Let a, my machine is giving a lot of problem. Let a equals to 9. This implies, so we have to start from 9, because we cannot take a equals to 10, because if we take a 10, then we can see that 10 into 10 is 100. It is becoming a 3-digit number, but we have to consider only the 2-digit number, largest 2-digit number, which is a perfect square. So a equals to, if we consider a equals to 9, this implies a square is equal to 9 square, which is equal to 81, which is of course less than equal to 99. So the answer is, find the largest number of 2 digits which is a perfect square. So the number is 81. We have to keep on finding the largest a such that a square is less than equal to 99. Now what is problem 6? It is the same, but we find the largest number of 3 digits which is a perfect square. 3 digits, perfect square. So the largest 3-digit number is 999. This was largest 2-digit number. Similarly, 999 is the largest 3-digit number. We have to consider all numbers which are less than equal to 999. That will be a perfect square. Now, similarly, we have to find a such that, find a such that actually find a largest a such that my handwriting is not coming properly because the machine is running very slow. Find largest a such that a square is less than equal to 999. Now what is the maximum value of a we can consider so that its square will be less than equal to 999? Can we take So how many digits can A have? 3 digits? No. If can it be 100? Can it be 3 digits? 100? No, because 100 into 100 is becoming 5 digit. So can it be even 2 digits? Can it be 2 digits? Let's say the least 2 digit number is 10. 10 into 10 is 100. Okay, so 10 can be. Can it be 20? Can it be 20? So you have to find this way. So if A equals to 20 implies A square is equal to 20 into 20 equals to 400, which is less than 99. We have to make it as close as 999. We have to make it very close to 999. So let's say now you can say you can see 30. This implies A square is equal to 30 into 30, which is equal to 900. We are close. 9 which is less than 999. Now we have to be careful. You cannot consider A40 because 40 into 40 will be 1600, which has 4 digits. Now you consider slowly. Let's say A31. This implies A square is equal to how much is 31 into 31? This is 31 and this is 93. So 961. 31 multiplied by 31 is 961. We are still in the range. It is still less than 9999. Can we go a little further? Can we go a little more than A31? Let's see what if 32. This means A square is equal to 32 into 32, which is, let's say 32 multiplied by 32 is how much? 64 multiplied by 6, 9. No, it is crossing. It is crossing. 1024 is becoming greater than 999. So the maximum A that we can have, so that A square is less than equal to 999 is 31. So definitely answer is 31 square, which is 961. So this is the 961 is the largest 3 digits number, which is a perfect square. So this was my idea of solving the problems 5 and 6. I do not know whether there is any better method of solving these two problems. If you know, then you can let me know in the comment section. I will appreciate that. So this brings to the end of solving the exercise 3A. Even though I did not solve all the problems, I hope whatever problems I solved, it will help you understand how to apply the concepts of perfect square and the prime factorization method to verify whether a given number is a perfect square or not, and all the concepts that I have discussed in this video. I hope it will be beneficial to you. If it is so, then please like this video, share the video, and please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. So the next video will be about finding the squares of a given number, and then square roots of given numbers. The next topic will be on the properties of square numbers or perfect squares. There are a lot of properties, and then we will solve the exercise 3B that is based on the properties of perfect squares or square numbers. After that, we will move on to finding squares and square roots. So thanks for watching, and until the next video, take care and bye.